Okay, today we will cover the magnetic force. The first thing we need to do before covering the magnetic force is to review very quickly the cross product. So cross product, if I have a vector, say vector A and another vector B, for example, and I want to calculate the vector A cross B, which is another vector C, there are two properties for this cross product. The first thing is the cross product, the result is a vector, and this vector is always perpendicular to the plane formed by A and B, by the first vectors. So, and then another important thing is the direction of this vector. So the direction of this vector is the following. A cross B gives you C. So A cross B. So if you move A to B, you are doing a clockwise. And when you are doing a clockwise, then the vector C is into the page. So it's perpendicular to the plane formed by A and B, but it's perpendicular. But it's into the page. For example, if you want to do B cross A, then it will be another vector D, but then B cross D is this way, so it will be out of the page, which means that C is equal to minus D, because they are equal in magnitude, but opposite in directions because of the way you are doing it. A cross B is equal to minus B cross A. And this applies to any vector. If we have vector A and B, even if they are not perpendicular to each other, so A cross B will give you vector C. And this vector C will be into the page. Okay, or perpendicular into the page, perpendicular to the plane formed by A and B. Okay, so the vector C or the cross product always produce the third dimensions. Okay, so the magnitude of A cross B, the magnitude of vector cross product A cross B is equal to the magnitude of A, magnitude of B, and then sine of the angle between A and B. Okay, so this angle, for example, let's say theta, this is theta. So now let's go to the magnetic force. So if we have a magnetic field, a region of magnetic field, and we have an electric charge, so an electric charge Q, that is moving with velocity V, and that is entering a region of magnetic field, this, and it entering a region of magnetic field, let's say there is a region of a magnetic field here, we'll talk about the direction later, and this charge has a velocity V, so this charge will undergo a magnetic force that is equal, so the magnetic force that we'll call P is equal to the charge, the cross product of the velocity cross B. Okay, so this is the magnetic force. Now the directions of the magnetic, field, force direction, of course, depend on the cross product. Depend on the cross product V cross B, as we mentioned, V cross B, but also depend on the sign of the charge. So the force, the magnetic force on a negative charge is different, or is opposite sign on the one exerted on a negative charge. Okay, so let's give an example. Let's assume I have a particle moving with velocity v, and the magnetic field is in this way, b, and then let's assume this is a proton. This is a positive charge. Let's assume that this particle is a proton, which has a positive charge. So since it has a positive charge, V cross B will give me a force that is out of the page. Okay. Now let's assume that I have now, for the same magnetic field, I have an electron. And now I have an electron. So this electron is entering the same region of magnetic field. But now what happens is that because of the charge, so V cross B will give me a vector that is out of the page, but because of the negative charge of the electron, it will give me a force that is into the page. Okay. So for example, give an example. Let's assume I have, well, this is an example. I have, let's say this is X. This is the X axis, Y axis, and then Z axis is coming out of the page, which means this is I, this is J, the unit vector, and K is coming out of the page, K. Okay, so let's assume I have a particle that is moving with velocity that is equal to V0 J. So the particle is going upward, and let's assume that there is a magnetic field, and this magnetic field is along the Z axis. So the magnetic field is going this way. Okay, so what will be the and let's assume that this is an electron. So this is an electron. Okay, so the magnetic force created on this electron is equal to the charge of the electron times the cross product V0J cross V0K. This will give me Q V0 J cross K. So I know that I can easily see that J cross K will give me I. Okay, J cross K will give me I, and because the charge of the electron is equal to minus the minus E. E is we know that 1.16 to the minus 19 Coulomb. So then the magnetic force created on the electron will be minus E V0 B0 I. Okay, so the magnetic force will be going to the right. So this is the magnetic force created on this electron. Okay. Okay, let's start. Consider again the force, magnetic force on a charge particle that is moving with a constant velocity v. So this particle will enter a region of magnetic field, and this magnetic field is pointing toward the page. So this means that there is a force that will be upward. So an interesting phenomena that happens here is that this particle will undergo a circular path with radius r that we can easily calculate. In fact, the particle is subject to this centripetal force, and due to the second law of Newton, we have, let's say, F is equal ma, where a is the radial acceleration. We can easily see that the magnetic force QVB is equal to mv squared over r, because AR, the radial acceleration, is equal to the velocity squared over the radius of circular path. So this will help us to get the radius as a function of the mass of the particle, the velocity of the particle, of course, the absolute charge, the absolute value of the charge, and the magnetic field. This is the radius of the circular motion to which the particle will be subject to when it enters the magnetic field, or the region of the magnetic field. For example, if we have an electron, so an electron of kinetic energy 1 keV, so the kinetic energy of keV, and this electron enters perpendicular to a magnetic field region, and this magnetic field has a strength of 10 to the minus 4 Tesla, for example. So one question will be, what are the period and frequency of its circular motion? So we are talking about the period and frequency excuse me, about the circular motion. Okay, well, we know that, so we are talking about the period and the circular motion. So we know that one full path, one full circle, the distance that the particle will do during one full circle, which is 2 pi r, is equal to the velocity of the particle times the period, which means the period is equal to pi r over v. But we also know that r is equal to the mass, the velocity of the particle, the absolute value of the charge, and the magnetic field. So this gives us a direct, combining this equation, let's say I will call it equation 1 and equation 2, will give me the period equal to 2 pi m divided by the charge p. Okay, so this will give me something like 3.6 10 to the minus 6 second. Obviously, the frequency is equal to 1 over t, and this will give 2.8 megahertz. Okay, now we can also calculate the velocity. So another question will be, what is the radius r? Well, we know that the radius r is equal to mv over qb. Of course, I'm taking q as the absolute value of the charge. So we need v. In this equation, we need v. But v, we can obtain it from the kinetic energy. So the kinetic energy is equal to 1/2 mv squared, which will give v is equal to 2k over m square root of v. Okay, 2k over m, and we have already the kinetic energy because it's given. So we can easily calculate the velocity. Okay, and the velocity will give us the radius, which is mv over qp, and the radius is around 1.1 meters.